Okay, here we go. Here's the second part of the lecture on 7.1, 7.2 about solving linear equations. And then here are the objectives. And what we're going to do is, I'm going to go through all this, so we want to dive a little bit deeper into the solutions and what the connection is to graphs. And then we're going to show that you want to know when the graphs of these lines associated with the system of linear equations intersect, and there'll be one solution. And then when they're parallel, and when there's parallel, there's two possibilities. They're either on top of one another, and that means there's infinitely many solutions, or they don't touch at all, and that means there's none. So, like I say, we'll go through this. Okay. So there's some terminology involved too. A system is said to be consistent when there's at least one solution. A consistent system with exactly one solution, which is the examples we've seen so far, is called independent. And if you have more than one solution, then it's called dependent solution. So independent, one solution. Dependent here is going to be infinitely many solutions. And then inconsistent means no solutions. So we'll look at some examples. Okay. So here we have dependent, and you see that here in a dependent, it's just one line, so it's the same line. Here, if you have inconsistent, you're going to have parallel lines, so they don't touch. You can see here, and then over here you're going to have intersecting lines. So these lines would go something like that. They'd intersect in a point. Okay, so we'll go through all these. Okay, first of all, whether it's just a single line. Now, how are you going to know it's just a single line? By looking at it. Well, you don't really need to, but you're going to discover it when you do your work. So the first thing I'm going to do is I'm going to notice that, if I multiply this by -2, I'm going to get -4. And so the x coordinates will be the same, and we can eliminate them. So that's why I'm going to use elimination right there. Okay, so I'm going to go through the work below. First line, multiply it by -2, and I get -2 times 2x is -4, -2 minus 3 is 6, and then -2, 3 is 6. So this first line becomes 4x plus 6y is equal to -6. Now guess what? That's the same as this. So that's supposed to say same, not same. Okay. Now, so since they're the same, I'm going to add these and see what happens. That's usually a good thing. Now, when they add them, something strange happens. Now, that's strange, but when it happens, when you get 0 is 0, it turns out that the lines defined by the equation are the same, and you have two lines, not one. So this is important. I'm going to say this is true. That's a true statement. 0 is equal to 0, and that's why it's consistent. So I'm just going to abbreviate it here with consist, and that's dependent. Oops. So consistent and then dependent. Okay, good. Okay. Now, so we're in this situation right here. So I just want to talk a little bit more about this. Just to review, we solved those. We got 0 equals 0, which is a true statement. So really what it means that these two equations are the same, right? And so there's just one line. So if I take any point here and plug it in here, it's going to work. And if I take that same point and plug it in over here, it's going to work there as well. So any point on this line is going to work for both of these. And how many points are there on the line? Infinitely many. Okay, so you have infinitely many solutions. And right here, what I did was I took two of them just to show you what happens. I plug 0, -1 into both of these equations. So I get 2 times 0 minus 3 minus 1. Is that equal to 3? Yeah. 0 is indeed equal to 3. And I do the same thing here. I plug -4 in for 0 here. Plug -1 into 6 here. Is that equal to 6? 0 minus 6. Yep, that's true. And then I do the same thing over here. I plug 9 for here and 5 for here. So I get, is that a true statement? Well, 2 times 9 is 18, minus 15, 3. Yep, true. And then I do the same thing here. I plug in 9, 5 into the second equation. I get minus 36 plus 30, that's minus 6. Yep, true statement. Okay, good. So, yes. So, again, you could take any point on the line and you'll see the same thing happens. Okay, so now we go to the second situation where the lines are parallel. And again, this will come out when you do the work. So we're going to go here. Now I notice the same situation here. And I notice here that I can eliminate if I multiply both sides here by minus 2. I'm going to do the same thing again. And so, and then what I get, so I'm going to do that down here. I take the first line, multiply it times minus 2, and then I do the math and I get 4x minus 6. So this is really here, this is 4x minus, sorry, plus 6y equals minus 6. And they're not the same. Notice that those are different. So they're not equal. Okay. So again, so what I'm going to do here is I'm going to take the equations, I'm going to subtract them, because to get that rid of that will cancel, this will cancel, and I get a 0 on the right side, but I get minus 6. So I get here, and notice this is a false statement. And then this is inconsistent. Right? False, inconsistent, they mean the same thing. Okay. And then here there's no solutions. There's none. Okay. Now why is that? Well, we're going to see on the next slide, the situation looks like this. Okay, so let's show. But the bottom line is, anytime you get a false statement, here, let me do this here, that's going to mean that it's inconsistent and no solutions. So keep that in mind. Okay, let's go to the next slide. I'll organize it. Okay, so this is summarizing what we did before. We tried, and we got 0 equals minus 12, so we know there's no solutions. So what I'm going to do is I'm going to solve for y in each equation. So I'm going to start with the first equation, and then I'm going to add 3y to both sides. That gets rid of this. And so that leads me to this right here, this new equation. Now I'm going to subtract 3 from each side. That gets rid of this. And so I'm in this new equation here. I want to put y on the right side, so I do that here. And now to get y alone, I solve for 3. I'm sorry, divide by 3. And that's what I have here. And then I simplify, and that's what I get here. So that's my equation for the line. This is the line that belongs, sorry, I don't want to do that. Oops. This is the line that belongs here. Okay. Okay, so here notice that my slope is 2/3. And then b is equal to minus 1, and that's the y-intercept. The y-sept. And then that's going to be this point right here. So that's line number 1. And b here is minus 1. Okay. So we do the same thing here. I'm not going to go through all the math, but I solve. Oops, let me get this right here. And I'll let you go through this if you want. And then I have another line. Same slope, but a different y-intercept. Here b is 1. And so that's going to be this again, remember, and this leads down to here. So here I have line number 2, and my intercept is 1. So again, I have parallel lines, no solution. They don't touch. Okay. So the next one is the situation we did in the previous lecture. So I'm going to go through it, but I think you should know it pretty well. So I'm going to solve for x in this equation. I'm going to use and then plug it back into this equation and solve. So here, take that first equation. I solve for x. I just subtract minus 2y from each side. And that's what I get. X is minus 5. I'm going to plug this in here, which right there is going to be right here. And 2 minus 5y minus 3y. And then the next step is I get this. So I'm going to combine the two y's here. So I'll do that here. And now I subtract 10 from each side. That's going to cancel. This is going to be a minus 5 over here. So you'll see what I get right here. So I get minus 5y is equal to 5. Divide by 5, minus 5 each side. And you see that I get y is equal to 1. Okay. So now I want to plug this back into my equation. So I'm going to plug that in here. And that's what I do here. X is equal to 5 minus 2y. That means that x is going to be equal to 5 minus 2 times 1. I do the math here. I see that x is equal to 3. So my solution is this. And that's going to be this point right here. Okay. So again, the key is here, is that each equation has two lines associated. This is where you have the same line, and you have infinitely many solutions. This is the second case. The lines in the two equations are parallel, and you get no solutions. And then the third case over here, oops, here, let's turn that off. Third case over here is you get the lines intersect, and you get one solution. This is supposed to be two lines, so let me make that better. Boom, there's one line, and there's the second line. Okay, and you have one solution. Okay, now we're going to do an application, and the application is going to be kind of complicated, so just be patient. And what I want to talk about is a little bit is how do you know that a word problem, if you're not being told in advance, means use two equations? Well, usually what you're going to have is you're going to have two unknowns that aren't related to each other. They're independent. So that's going to be the biggest thing, two things you're looking for. And often there's going to be two parts. Like there's going to be two things going on. So here's what I mean. Here's an example. So here we have two things going on. So I'll read the problem. An airplane flying into a headwind travels the 2,000-mile flying distance between Chicopee, Mass. And Salt Lake City, Utah in 4 hours and 24 minutes. Okay, on the return, it's 4 hours. So this is one thing right here. And then this is the other right here. So 2 hours, okay. Now on the return flight, the plane travels this distance in 4 hours. Find the airspeed, and that's going to be the first unknown. And the speed of the wind, that's going to be the second. Okay, so again, I'm going to read it again. I think it's good to do that twice, because especially since I was talking a lot, and then go back and look over it. An airplane flying into a headwind travels the 2,000-mile flying distance between Chicopee and Salt Lake City in 4 hours and 24 minutes. On the return trip, the airplane travels this distance in 4 hours. Find the airspeed of the plane and the speed of the wind, assuming that they both remain constant. So there's the two unknowns, the airspeed and the speed of the wind. They don't relate to one another. They're two completely different things. And then we have the two trips. Okay, so here's what we got. The two unknown quantities are the speeds of the wind, and I'm going to call that R2, and the speed of the plane, R1. And so if you want to know the speed of the plane with the wind, you're just going to add the two things right here. It's this plane speed plus wind speed. That's how fast you're going with the wind. Imagine the wind at your back. Now imagine walking into the wind is going to slow you down. So when you go against the wind, it's your speed minus the wind speed, so R1 minus 1, 2. So we'll go to the next slide, and this next slide just has a picture of it right here. This is sort of repeating the same thing. Speed of the plane with the wind, you add them against, you subtract. So here see why you subtract in the original flight, and here return flight. So this is going to be, by the way, this is going to be one equation. This is going to be equation number 1, I believe. And this is going to be down here, so I'll turn that off. And down here, turn that off. Oop. And this is going to be equation number 2. Okay. So again, the flights are each equation, and then the variables are the speeds. Okay, so we'll go to the next one. Again, there's some work in here. So the formula is going to be distance times speed. And I want to go over why this is true. Distance is d. Speed is distance over time. And that's going to be times time. So t times d over t, the t's cancel. So that's why time times speed is distance. Okay, so here's the first equation. It's the flight out there where you're against the wind. So it's plane speed minus wind speed times time. So speed times time. And then on the way back, it's going to be something similar. It's going to be speed times time. Okay. So I want to look at this first equation and tell you where the time comes from. Remember that 24 minutes is 24 over 60 hours. So 4 hours and 24 minutes is this. Okay. So now I want to reduce the fraction, and I notice that 24 and 60 both have 12 as a factor. So I write 24 as 2 times 12 is 5 times 12, and then I cancel those 12 and I end up with 2/5. And then 4, I got 2/5 here, so I want to write 4 in terms of fifths. So I multiply by top and bottom by 5, and I get 4 is equal to 20/5. And so 4 plus 24 60th is the same as this. And then if I add those together, I get 22 over 5. So that means I can rewrite equation number 1, go through here, as this. Oops, sorry, let me do that here. And then now I multiply these things, and this is what I get over here. So when I multiply, I get this. So, oops. And then to simplify things and restate, here's equation 1. And then here's equation 2. So now I have my 2 equations. Now, this doesn't look great. I'm going to use elimination, but I'm going to do some algebra. I want to simplify this equation, get rid of the fractions, and simplify this equation. We really haven't done much of this, so I'm going to do a little bit of it here. So bear with me. Okay. So again, I want to repeat what the problem is. But we have these 2 equations, and now we're just going to solve these. So I want to get rid of the 5. So what I'm going to do is I'm going to multiply both sides by 5. And I get 5 times 2,000 is 10,000. 5 times 22 over 5 is going to be 22 R1, and 5 times 22 over 5 R2. The 5s cancel, and then I'm going to get 22 R2. This one I don't do anything. So that's my new system right here. And then what I want to do is I want to simplify this. I notice that each of these has a factor of 2, so I divide everything by 2. And when I divide that 2, I get 10,000 by 2 is 5,000. So this is my new equation over here. And then I notice that everything here has a factor of 4. I can divide 4 into everything. So I do that, and then here's my second equation right here. So this is my new system right here. And I'm going to use elimination, and so what I'm going to do is multiply both sides here by minus 11. Okay, so we'll do that on the next slide. And here we go. So I'm going to multiply both sides by 11, and then add them. Sorry. Okay. So I start here. I multiply this by 11. So I get 11 here, and then 11 times this. So 11 times this is going to be 5500, and then 11 here is going to be there. So this is what I get right there. It's my new, and if I add these, notice I'm going to cancel out the R2. And so I get 22 over R1. So now I can just solve for R1. I can just divide both sides by 22. I'm going to do that in the next slide. So R1 is going to be 10,522. You don't really need to go do this one, but this is what I get for my answer for R1. And now I want to find R2, and I'm going to use this equation here. So here's what I do. I know that this is true, and so I'm going to subtract R1 from each side to get R2. So I'm going to subtract minus R1 here. Sorry, let me do it again. Subtract minus R1 here. That cancels. And so I get 500 minus R1, R2. And that tells me that, here, I don't need this here. This is a mistake. So R2 is 5,000 minus R1. Okay, so that's what I'm going to use. So I'm just going to plug this right into here. This is what I do here. 5,000 minus 477.23. I do the math. Again, you don't need to do this. Just use your calculator. And then you're going to get the wind speed is 23 miles an hour. So that's the solution. Okay, so that's a hard one. So feel free to go back over that and ask questions. Okay, that's an involved one. There's a lot of algebra in that. So anyway, I hope that makes some sense. Again, it's a hard problem. Okay, so I'll be happy to answer questions of this in office hours or in class. So just let me know. Okay, bye-bye.